So when compared to rectangular and triangular interlock switcher, spline regression model gives a high significant value 0.992. So that I took spline interlock switcher as the best interlock switcher, and I perform optimization for that regression model using particle swarm optimization techniques. So this is a behavior level biomimicry. That means inspired by the foraging behavior of birds and fishes in search of food. It was developed. The PSO start with particle, number of particle, and initial velocity and 0, position also 0. And by evaluating the bending load by using the regression model, local best is identified, and then it is compared with the global best. Similarly, and next the velocity and position is updated. Again, the local best is identified and is compared with the global best. So like that, it goes until it reaches the maximum bending load value. Once it reaches the maximum iteration or bending load value, it stops. So I wrote a PSO particle swarm optimization code in a MATLAB software. The code is here with velocity equation. Here you can see the 190 to 210 value. Here 30 to 60 speed and 0.1 to 0.3 layer thickness. So the PSO code was written in MATLAB software with several combination of values, iteration values, as well as the random particles, with inertia factor of 0.05 and self-confidence of 0.1 and swarm confidence of 0.1. The results are same even I increase the iteration beyond 1500, as well as if I increase the value beyond particle value beyond 50 also, I get the same answer. So this is the PSO result. Here you can see 190.3, 60.5 and 0.1 layer thickness. If I maintain these three optimum values, means I get the maximum bending load of 345.28 Newton. So this is for a 50 number of particle with maximum number of iteration 1500. So to validate the PSO result, I perform RSM, response surface methodology also. So the results shows that the same thing, 190 and 60 and 0.1 gives the maximum bending load of 345 Newton. 345 Newton. And then I wrote one more code, one more biomimicry behavior level, that is called optimization technique, hydrotropism optimization technique. Generally, tropism means in biology, which indicates a growth or turning moment of any organism towards any stimulus. For example, if we take plant, if it respond to light, means it is called phototropism. If it respond to water, means that is called hydrotropism. I inspired by this behavior, foraging behavior of roots in search of water, that is called hydrotropism. I developed one algorithm to solve optimization problems. Here, this is how the hydrotropism works. Consider this is a search space. So once it identifies the water, the root will grow towards that direction to find that moisture or water. So let us assume this is our solution, and this is how it find the water. So this is the root anatomy. Why I use taproot system is taproot system go deeper and it will find water even in a dry place. That's why I choose taproot anatomy with primary root, tertiary root and secondary root. So this is how it works. So let us assume this is a workspace and this is a tree with taproot system. This will find water. So HOT algorithms start with initialization, like it starts with primary root. This is let us assume this is a search space. It starts with primary root with 3 nodal points, and from that primary root, 3 nodal points, secondary root will develop. So you can see secondary root with 8 nodal points over here, 8, 16, 24 nodal points. And then what happened? Once it find the minimum value in each layer, top layer, bottom layer and middle layer, from the center nodal point, again the root will develop to that point. So this is called tertiary root nodal points. Once the tertiary root is developed, root hairs also developed. So you can see small yellow colored dots are called root hairs. So root hairs developed randomly, nearly 30 nodal points per tertiary root, means totally 90 nodal points are developed. So now what happened? These nodal points, the best value from all these nodal points, nearly 90 nodal points are compared and find the best value. Here let us assume this is the best value compared to 90 nodal points. So now what happened? Root hairs will develop here. Root hair development will take place with factor 0.3. So this 0.3 indicates the size of the root hair. If I increase the 0.3 to 0.8 means the root hair will grow like this. So if we want accurate solution, we can reduce this root hair to 0.01 itself too. So root hairs. Again, the same concept is repeatedly happening here in this small search box. Again primary root, tertiary root, and again root hair will form, and again this root hair will grow here. So like that it will search in this space to find the best solution. This is how the hydrotropism optimization technique works, and this is the code written in MATLAB software. This is the HOT result. So 190.60.1. So now I compare the results. You can see all these three optimization techniques have an ability to find the maximum bending load value. So all are same, 345.28 Newton. To validate the PSO and HOT code, I took one regression equation from a journal where they optimize the process parameter of milling parameter to improve the surface finish. So they took parameter cutting speed, feed rate, and radial rake angle at these levels, and they developed one regression model. So what I did is I took this regression model and this level, and I use so in this journal they use genetic algorithm and RSM to solve this problem. So Mohruni is already solved the same regression equation in 2008 using RSM technique. He get this value using RSM technique. And Zain at 2010 used the same regression equation, and he come up with the answer 0.138 using a genetic algorithm. And now I use this regression equation and the range, and I come up with this answer, same answer 0.138 using HOT technique. So it's similar to it's equal to genetic algorithm. And I test the same regression equation with the MATLAB code also, PSO written code also. It come up with the answer 0.129. So when compared to all other optimization technique, PSO gives the best value. So from that, what I conclude is the code written in MATLAB for PSO and HOT have an ability to find the best value. So here the video, how it works. So without interlock suture, you can see it will break suddenly. Without interlock suture, this is how it breaks. So without interlock suture, what happened? It will break suddenly. These are FDM components. This is how it breaks. So with interlock suture, so even breaks, it will not come out. Similarly, here you can see the same FDM component printed with spline 3D interlocked structure. So even you can see the deformation, even it breaks, it will not come out. So that's the inspiration. It exactly break like a branches. So the conclusion here is I identified three different interlock sutures, 3D interlock sutures. One is spline, and then rectangle and triangle. And I perform a design of experiment. Nearly 48 experiments were fabricated here, and these are tested. And then I develop regression model for all these three interlock sutures, and I select best interlock suture by performing a t-test, and then I use that regression model to for optimization. I use RSM, PSO, and